So my name is Josh Patterson. I'm the Director of Engineering for RAPIDS. RAPIDS is NVIDIA's open source platform for data science. So I'm talking primarily about RAPIDS and what it does, why we built it, and just some of the business values of it. One of the things I love about the conference today so far is about putting all this different machine learning in production. And the thing that we really realized quickly early on at NVIDIA was CPUs were kind of running out of performance, and we really had to make things faster so we can do more iterations. And we started with deep learning, and everything was going really well, but there's so much more to data science. There's data frame processing, there's array processing, there's graph analytics, there's traditional machine learning. And so one of the things we want to do is build an ecosystem of software that allow people to do all these things, but without having to learn new tools. And so first I'm going to start off with the foundations of this, which is Apache Aero. When we first started, we've been building big data platforms for several years now, and most of my time has been spent in cybersecurity before joining NVIDIA. And so we started with Hadoop, and then we moved to Spark, and we got a massive improvement for things. One of the things is data keeps growing. So as our cybersecurity platform kept growing, we needed to process more data, and we really started to hit some of the limitations of what we could do with things like Spark. And so then we moved to GPUs for just graph analytics, so just running PageRank across our data so we could build a time series model of centrality scores to really figure out anomalies in our networks and other type of cybersecurity metrics. And the results were really great, and we had better machine learning models. But what we realized was we could run PageRank really quickly, but everything else was really slow. And so we started to think, how could we move more things to the GPU? And so one of the first things we did, we started working with OmniSci, at the time called MapD. It was an in-memory GPU database. And so we could do these sub-second queries in MapD, and then we were moving the data to graph history, a graph visualization engine, and it could also render these million, 100 million edge graphs in seconds. And so we could do these real-time cyber hunting. The problem with this was going between these two systems that were both on the GPU would take almost 2 minutes. So I could run a query sub-second, and then if I wanted to visualize it, I would have to wait 2 minutes. Put this in perspective, for Gephi to do this visualization would take about 30 minutes, and for Spark, even on a 50-node cluster, it was taking about 1.5 minutes. And so we were getting this great speed up, but the data movement was killing us. So one of our first goals of RAPIDS was to really remove the bottlenecks of moving data back and forth, create standards of how we can represent data on the GPU and keep it on the GPU. At the same time, Apache Aero was coming around. And so Apache Aero set the standard for a columnar data representation on CPU, but it was also great for the GPU. And so Aero, which is language agnostic, so it has Java, C++, C, Python, R, Ruby bindings, we can also use it natively on the GPU with Cuda C++ and Python. And so once you put this all together, we now have a way to represent data on the GPU. And everyone knows how to read and write this data on the GPU, so we can leave it in memory and just pass pointers. And now that we have these really, really fast engines, and we can pipeline them together, so we get this 50 to 100x acceleration, primarily because we're not moving data off the GPU. And that was really the biggest breakthrough that we had. And everything after that is us just trying to complete out the ecosystem. So here's a real world example. We were working with a bank, and so we can't show their data. So what we did is we downloaded all 200 gigabytes of data from Fannie, their 2000 to 2015 mortgage records that they make publicly available. And this data set has two data types. One is acquisitions and one is their performance. And so what we did was we combined these two data sets, so just some common joins, then we do some group bys and some other transformations to get these characteristics of borrowers. How do they perform 1 year out, 18 months out, et cetera. And then we built a model that would predict if a person would either prepay or default on a loan within a year. And so as you can see, the really long bars are how long this would take in Spark, and the shorter bars were us doing it on GPUs. And the cost parity is around 40 nodes. And so on GCP, 40 nodes is roughly the equivalent price of 16 GPUs, a DGX2. And you can see this order of magnitude improvement dollar for dollar. And that's really what we're seeing more often than not, is this massive acceleration at the same cost. And so why this really matters is basically, the more iterations you can do, the better as a data scientist you become somewhat magically. Francois Cholet, he had this really great talk at AnacondaCon, and he had a series of tweets, basically just saying, what separates a good data scientist and a great data scientist is time and iterations. If you have a really good tool like scikit-learn or Keras, people know how to use it intuitively. So then they just need to iterate. They need to understand their data, ask a question, and iterate. That iteration cycle, the faster you can do that, the more times you can do that, the better answer you'll get. And anyone can do this. And so if anyone can do this, and we just need to give people familiar tools and make them faster, we decided to really kind of do that, but at a larger scale. So RAPIDS at its core is literally the PyData ecosystem, changing no APIs, but we're going to add GPU acceleration. So I'm going to go back and forth real quick. cuDF, which I'm going to talk about, is our data frame library. It's pandas. cuML, scikit-learn, cuGraph, NetworkX. We literally take the pandas API, the scikit-learn API, the GraphX API. We do all the plumbing under the hood. So you change no codes besides your import statement, maybe a few lines here and there, and you just get native GPU acceleration with custom CUDA kernels that are optimized for different types of data, different types of problems. And under the hood, we handle all of the complexity of generating new kernels, fusing kernels, what have you. And then we have hand-optimized kernels, but it all plumbs up for the user in this simple Python API. And then we use Dask to scale this. And so we spread Dask across cuDF, cuML, and cuGraph, really to leverage multiple GPUs across multiple nodes. And why Dask? So we get a lot of questions about Spark versus Dask, and I think there's a really great blog about this. One of the reasons why we wanted to work with Dask is because A, of its HPC nature, and B, because it's not a compute engine. It's literally just a scheduler. So it takes these PyData libraries like pandas, scikit-learn, and it parallelizes them across cores, across nodes. We wanted to do the same thing, but instead of across cores, across GPUs. So out of the box, things just worked, which is really great. One of the things that didn't work, though, was communication. Dask had no concept of how to use things like NVLink, which is our fast path between GPUs that's about 10 times faster than PCIe Gen 3. It didn't have ways to leverage InfiniBand natively. But because it was born out of HPC, there's another HPC project called OpenUCX. So OpenUCX is, think of MPI, but one level lower, where it's basically just point-to-point. And so what we did is we added Python bindings to UCX. And this is finally is going to be released in our next release in 0.10 in a few weeks. And essentially, we can natively use NVLink, NVSwitch, InfiniBand, Rocky, all these high-performance ways of communicating across GPUs natively in Dask. And we just replaced Dask socket communication with this fast path communication layer. So now we have GPUs doing things really fast. We can communicate across all the hardware acceleration, InfiniBand, whatever you have. And now we can do really, really large-scale computation quite simply. And so we scale up with RAPIDS, and then we scale out with Dask and UCX. So cuDF. The cuDF technology stack is pretty simple. We have Cuda at the bottom, then we have Cuda libraries like Thrust and Cub that we build on top of, and then we write cuDF C++. So this is libcuDF. libcuDF is our C++ layer where we write things like sort algorithms, hash-based joins, sort-based joins, hash group bys, squirt group bys, so forth and so on. And then we use Cython to bind that to the Python level. And so in the Cuda C++ layer, as I said, is really just, this is where all the hard work and all the engineering happens, is we make sure everything is really fast at this level. And then we use Cython to plummet to this level. So end users, they see something that looks like pandas, that follows the pandas API, and we do regular testing against pandas. And for anything that's not in the Cuda C++ layer, we use something called Numba. Numba is a just-in-time compiler for Python that then allows you to generate a kernel that runs on the GPU and still gives you native performance. And here's some benchmarks of just kind of how much faster this is. For joins, comparing 40 cores versus a single V100, it's about 800 times faster. And this is on 10 million rows. And you can see on the chart group by, sorting, and the different speedups. We also added in a full string library as well. So you can things like split, concatenate, upper, lower. basically full string functionality that you would find in pandas. You can also do on the GPU. It's also roughly 100 to 200 times faster than pandas. And then we also added data loading. One of the things that we realized very quickly is once you can do all this computation 800 times faster, the biggest bottleneck was loading the data. So if we didn't do these data parsers, we would spend 90% of our time just loading the CSV. So we added readers. And then as soon as you add readers, the next thing you realize is you need writers. So far we've added CSV, Parquet, Org, JSON, and Avro. And on the writer side, CSV and then Parquet and Org will be released in our next release in 3 weeks. Again, we're seeing about a 15 to 20x improvement, dual socket to single GPU improvements on the readers. And so this really allows us to scale to really large data sets. One thing that's not in this talk that we've been blogging about recently is GPU direct storage. Where we're going is not released yet. It'll probably come out towards the end of the year, early January, as a way to read directly from network attached storage. And so think of things like your really big storage like NetApp, Pure, DDN, IBM, being able to read directly from your storage flash arrays directly to the GPU memory, bypassing everything at speeds per GPU that's 20 times faster than CPU. And the benefit of this as well is with GPU direct storage, we almost get another 50% speed up because we don't have to worry about the system memory buffering. And it's actually kind of insane to think that we can read from network attached storage faster than we could read from system memory on a GPU. And so it's really just kind of getting these orders of magnitude speed ups. And so when you think about a machine that has 8 or 16 GPUs, each of them are reading 15 to 20 times faster than the CPUs, and then we're getting another 50% because we can read it directly across the network, you can start to quickly read in petabytes of data very quickly. And then finally, Blazing SQL. So Blazing SQL is a SQL engine that's built directly on top of libcudef, our C++ layer. So not only is the RAPIDS team building these Python bindings, we also have others in our community building SQL directly on top of CUDA and getting some really amazing speedups over Spark SQL. And it's not just data frames, we also have arrays. And so there are 15 CUDA Python array libraries that I know of. I think there's 16 because I heard of a new project recently. And we didn't want to create the 17th. So what we want to do is bring everything closer to RAPIDS. And we do this with the CUDA array interface and DLPack. So if you're using PyTorch, Chainer, MXNet, Numba, or some of these other array libraries, if your data is already in a data frame on the GPU, you can immediately pass to these libraries. You're not copying, you're not converting your data. It's literally passing a pointer. It's essentially instantaneous. And we can also scale this array computing out just like we do with the data frames with Dask. And so similar to Dask, how it has this concept of breaking arrays down into these distributed arrays, we can do this with Chainer and CuPy and Numba. And again, 1v100 compared to dual socket, we're seeing up to 100 times more performance. And then the beauty of this is we can also parallelize this across GPUs in a single machine and then across multiple nodes. Here's a 2-node example of this. So we basically just wrote a simple TSVD using NumPy. And so using all 40 cores, it takes about 600 seconds. If we move that to 1 GPU, it takes about half the time. We can then use 8 GPUs, and that drops it down by roughly about 6x. And then we can do this across 2 nodes, and that drops it down almost in half. Another way to think about it is that we want to use these arrays to do some type of aggregation. For a terabyte data set, a single core using NumPy takes about, I think it's that, I can't really read that, 2 hours, some really large amount of time. It parallelizes it very well to 40 cores, and it takes about 1.5 minutes. Moving that to 1 GPU, we're down to 1 minute, and then with 8 GPUs, about 20 seconds. And so you see this kind of scaling. And then we've done this out to about 3.2 petabytes on 80 GPUs, and we did the calculations in less than an hour. And so afterwards, I think the slides will be published where there's 2 YouTube videos, one using Dask and data frames and one using Dask and arrays. So QML. This goes back to what I was talking about earlier. What really makes data scientists really great is having more time, more iterations, less downsampling, more experimentation. The ML stack is a little bit more complicated. So we still start off with Cuda. We still have the Cuda libraries. But then we did something called cuML prims. What we realized is every time we want to write a distance matrix calculation, or we want to use a certain solver, or we want to use some type of GemV for a certain dimensionality of data, we didn't want to rewrite that every time. So internally, we were building these like primitives, and the ML team was sharing them with each other. We said, what if we, instead of just keeping this internal, we expose these and open source these as well? So all of our GPU primitives for machine learning, we expose these so anyone can build these algorithms on top. And so this summer, we actually had a bunch of interns and we tested this. And we had one intern who wrote TSNE just using cuML primitives. And it got state-of-art speed. And he did it in about 2 months. And he's never really worked with Cuda before. It was just a person who was a really good C++ programmer, right out of undergrad. And he's writing full Cuda algorithms because the primitives are so good. The great thing about this as well is when we improve the primitives, every algorithm that uses these primitives now just gets faster. So we come out with a new GPU, a new driver, a new kernel for these primitives. All of cuML just sees the benefit. And then on top of that, we have our algorithms, so they're also open source. And then we use Python to bind them to a scikit-learn-like API. And so this is what most people know today of what scikit-learn looks like. This is what it looks like with cuML. We also have these really nice cards downstairs if you get a chance. Basically, you flip them back and forth, and it shows a Cuda or Pandas code, cuML, scikit-learn. They're really fun. It's the same code. That's the gimmick, but I really like them. So go grab some cards, share them with your friends. It's pretty cool. Back to speed. It's fast. We have a lot of algorithms. One thing I'd like to point out is on one side, we're like scaling the millions of rows. On the other side, KNN and dbScan are so fast, they were just like, it's going to take too long to benchmark 1 million rows of these algorithms. So they said, can we just use a smaller subset for the algorithms where we're getting even more speed ups? And so we do a scale change from left and right, primarily just because the CPU benchmarks just took too long. So the next thing that everyone said, well, on the deep learning side, you have all these frameworks, and then you have TensorRT for deep learning inference. What if I have billions of rows and I want to do real-time inferencing for random forests, XGBoost, LightGBM? So we created a forest inferencing library. And so I'm going to talk a little bit more about this at the end. But essentially, 40 cores, 1v100, you're getting about a 30x improvement across the board for just doing inferencing on any forest model, any trees. And so today we have 3 algorithms that are multi-node, multi-GPU, a few single-node multi-GPU, and a bunch of single GPU algorithms. Our goal by March is to basically complete the primary matrix all the way out to multi-node, multi-GPU. And then the same with graph. Our philosophy with graph is we want to treat graph like a first class. It shouldn't be this thing that people just bolt on towards the end. And so with that, we want to basically have data frames and graph frames be the same thing. You can go interchangeably from CUDA directly into a graph. You can traverse a graph. You can run graph analytics. And it's always based around Apache Aero, so a COO. In the graph technology stack, we actually pull in a bunch of other libraries. There are 4 really good CUDA graph libraries. And what we didn't want to do was basically compete with them. So cuGraph is really an amalgamation of NVGraph, Gunrock, Hornet. We're working with Texas A&M for Graph BLAS, and we put it all together in one NetworkX-like interface, and then we pull the best of all these libraries into one place. And so whichever your favorite graph analytics library is, we expose it through a NetworkX-like API. And so we're really kind of amplifying the community by building an umbrella across the graph frameworks. In graph, we're seeing some really amazing speedups. Most of these are actually around 1,000x. And the next slide is really the one that I love to highlight. You can see the graph benchmarks and the speed up, but really the last row is the most interesting one. If you have a 300 gigabyte graph problem, this takes about 96 minutes with a 100 node cluster. On a single machine with 16 GPUs, you can run this in about 30 seconds. So an hour and a half, 30 seconds. for something 100 nodes is actually about 2.5 times the cost, of something that is roughly 200 times faster. So it really starts to add up doing these things. So if you know anyone who runs PageRank on 100 gigabytes of data, and they do it more than twice a day, they're not using GPUs, tell them you know somebody who can save them a lot of money. So here's where we are today. I know this seems like a Herculean jump by March, but we're spending a lot of time building these primitives. So all the things that we do on the QML side for communication and protocols and scaling will be leveraged on the graph side. So we're going to rapidly ramp up on graph functionality. So Nucleo. Why am I here? It's because, honestly, I love Aguazio, and I really love Nucleo. I'm sure you've heard about Nucleo, so I'm not going to explain what Nucleo is again. But when we talk about things like Cuda, we talk about the forest inferencing library, we talk about all these different models, being able to say, hey, I want to basically do a hyperparameter sweep of this model on this data, but then I want to change this data and do these permutations of feature engineering, and then I want to run inferencing on these, on the outputs of this XGBoost or random forest model. With Nucleo, I can make these just stages of serverless events. And so getting this in production with Nucleo is really easy. And there's a really great blog that's linked at the bottom, which is them just doing that. Taking CudaF, putting in the Nucleo engine, and then reading from Kafka or from their file system in Aguazio, and basically getting 30 to 100x improvement on a single T4 versus a dual socket system. And so I really love the concept of serverless. But serverless and GPUs were kind of these two different worlds that didn't really talk to each other before Nucleo. And then GPU acceleration and data science were things that didn't really talk to each other before RAPIDS. And so all these worlds are combining and coming together. It's just getting easier and easier to start deploying these things into real world applications. So with that, we have a growing community. We have contributors from many places: Walmart, Anaconda, Quansight, Blazing SQL. We have many adopters. We feed into many open source packages. A lot of the RAPIDS teams contributes directly to Apache Aero, XGBoost. We actually have 5 committers at NVIDIA that are 5 RAPIDS engineers, I should say, are committers to XGBoost. We have some who are committing to Apache Aero. We really believe in open source and also not like land grabbing things. So when we talk about CuPy, and as we add CuPy into RAPIDS, we make sure that people know that it's a chain or library. XGBoost, we've done a lot of optimization to make XGBoost faster, but it's still DMLC's XGBoost. We want to be good citizens in the open source community. We also have a lot of people building on top of RAPIDS. Nucleo, as I talked about earlier, Blazing SQL. There's also Streams, which is basically Spark streaming, but on Dask. And we have a lot of work where we're upstreaming some C++ integration into Kafka so we can natively read from a Kafka stream directly into CudaF without going through Aero. So it's pretty easy to get installed. If you've ever conda installed, you can conda install RAPIDS, you can conda install the whole Cuda toolkit, and you're pretty much off to the races in minutes. GitHub, we have a really great blog. YouTube channel, more examples on GitHub as well with some extended notebooks. And as I said before, Conda, GitHub, Docker Hub, NVIDIA GPU Cloud, which is our optimized set of NVIDIA GPU containers for different types of data science. All places where you can get RAPIDS. So join in. Even 5 months ago, when I would tell people, hey, this is really great, go try it. I was like, hey, this is really great, go try it, but it's going to break. And then tell me what happened, and then we'll fix it. I think we're at the point now where enough big Fortune 500s are using it in production, where it's go try it, go save a lot of time, report back some of the really amazing things you're doing. We had a really great GTC back in March where different people were talking about how they were using RAPIDS, and I was really amazed to see it from virtual reality to Walmart using it for forecasting. There's a bunch of banks and hedge funds using RAPIDS, so it's really become a lot more robust. We release every 6 weeks. We have an amazing team of engineers working on it. So go try it out. Contribute if you want. If you're a Cuda developer and you want to add a new functionality, there's a professor out of CNUI who helped with the Cuda spatial library. As I said before, we work hand in hand with Apache Aero, so contribute to that library as well. contribute back to Dask. Just really join in. With that, that's it. Thank you.
I may have missed the features for the pandas
We don't have a slide for that because the Pandas API is about 400 different operators. I would be surprised if there's an operator missing that you need, but if that is true, file an issue, and that's how we prioritize the new features. We basically have about 200 or so implemented today, and the ones that aren't are things that you can work around by either having 2 operators or doing some type of negation. But yeah, it's pretty complete on the Cuda side. Now we're mainly focusing on scale with OpenUCX integration, getting GPU direct storage in, and then really kind of large-scale testing right now. Sorry, I forgot to repeat the question. I know you told me to do that. He asked, what was the parity with Pandas API?
How about the, you did not mention, compared to maybe Spark, does it have any concern about throughput? How about, is there any theoretical limit on how big a data set can be?
No, actually. So one of the reasons why we talked about the 3.2 petabytes is kind of to show what's one of the larger things we've done, and that was only on 80 GPUs. For QML, most of it has to be in memory. Sorry, let me repeat the question first. Is there any limitation on the size of the data, he was asking, because Spark scales to really large data sets. On QML, there is a limitation. It has to fit in GPU memory. So we really designed it for problems that are in the 10 gigabytes to 10 terabyte range. We don't do out of core yet with QML. So everything has to fit in GPU memory. QDF fully shuffles between GPU memory and disk and system memory. And we've done very large scale things with QDF. QGraph is similar as well, where it's fully in GPU memory today, because most people's graph problems are hundreds of gigabytes. Honestly, the largest I've ever heard of was 5 terabytes from one of the European internet companies. And then after that, it's pretty much 3-letter agencies and intelligence departments who do larger graphs, and they have their own solutions. So I don't really worry about them. So if you have a graph problem that's larger than 3 terabytes and you're actively running PageRank on it, again, come talk to me because we have solutions for that as well. But it scales very large, especially on the data frame side. The scale on the data frame side is essentially as large as any other system. Machine learning, right now I'm going to just say 10 terabytes because that's probably our highest known range, but we haven't really tried much larger than that.
How hard is this to take advantage of this or something that's like on cloud, so like Kubeflow?
I removed that slide. We actually have Kubeflow integration. That was the first community that adopted RAPIDS. And the question was, how hard is this to run in cloud environments? Kubeflow was our first adoption. We have a great relationship with Microsoft Azure, and they have several blogs about how to run this one at Azure ML. GCP, both the DLVM as well as Dataproc. We have a blog coming out soon about AWS SageMaker and deploying RAPIDS on AWS. Alibaba and Baidu also have native integration with RAPIDS as well. Plus, every cloud has NGC compatibility. So NGC, our NVIDIA GPU cloud, we test every cloud and we have instances that can run NVIDIA Docker. So if you take our Docker image, you can deploy it to any cloud and it works. And so not only do we have integration with every CSP's ML services once we add the SageMaker support, we also have just a way to run RAPIDS from Kubernetes or bare metal in a Docker quite easily. So most of our customers start in cloud and then move on-prem. We have workstation options. So it's basically anywhere where you consume GPUs, this works.